Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at Newton's method. So Newton's method is a root finding algorithm that uses calculus. So geometrically, if we have a curve like this, remember its x-intercepts, these values here are all called roots. So Newton's method helps us find those values. So it's very useful in solving equations, and of course it can also be used to find maximum or minimum values, because we know that stationary points are just the roots of the first derivative. So how does the process work? Well, you start with some initial guess. I'm going to call it x0, and you find its place on the curve and draw a tangent to that curve. Now, then you calculate the x-intercept of that tangent and you go through the process again. You find where that is on the curve, you draw a tangent to the curve and find its x-intercept here. And you keep doing this until you reach a desired level of accuracy. So Newton's method is an iterative method. You start with an initial guess, which was x0, and then you find another possible guess, a better guess, which was x1, and then we call x2 the next guess, and so on. Each successive guess is the x-intercept of the tangent to that curve. Now we can see from this diagram, Newton's method often converges to the solution very, very quickly. There are a couple of times Newton's method doesn't work. For example, if your initial guess is bad, if we had an initial guess in here, we might not get this root, we might get another root, and also it causes problems if you end up with a tangent that is horizontal. So if we ended up with one like that, we'd be in trouble. But mostly Newton's method is a very, very good method because it gets you very close to the answer quite quickly. So Newton's method's based on this equation here. Hopefully you recognize this as the equation of a tangent. So let's say here that I want the x-intercept of this tangent. Well, of course, the x-intercept occurs when y equals 0. So replacing y with 0, we get this. So I want to solve for x, which would be the x-intercept since y is 0 at that point. So I would just subtract f of x0, then I'd divide by this, then I'd add that. So this would be the x-intercept of this tangent here. That's our guess, x1. So we can just make a more general formula. If you want to find the guess at the nth step, you just take your previous guess and you subtract the quotient of the function evaluated at that point and its derivative at that point. So again, this is an iterative method. We make successive guesses until we reach a desired level of tolerance. So let's look at an example. So here we're going to find the root of the polynomial x to the power of 5 minus x minus 1 using Newton's method. So just as there is a formula for quadratic equations, there is a formula for cubic and quartic equations. But they are so complicated, no one remembers them. That's why we use things like polynomial division. But it turns out there is no such formula for quintics. And sort of Galois showed why that was. So when you have polynomials of degree 5 like this, sometimes they're not solvable from radicals. Sometimes you can't just use combination of the 4 operations and square roots and the like. So the problem is we'll have polynomials and we have really no way to find their root. That's why we need numerical methods like this. So we're going to go ahead and find the root of this. So we're going to start with an initial guess. So I'm just going to start with x0 equals 1. That's going to be my initial guess. So now we have to calculate our next guess. So x1, it will be my previous guess minus the function evaluated at that point. So f of 1 is 1 minus 1 minus 1, which is negative 1. Now what about the derivative at that point? Well, the derivative of my function is just 5x to the power of 4 minus 1. So at x equals 1, the derivative is 5 minus 1, which is 4. So my next guess, x1 is 1 plus a quarter, which is 1.25. So now let's go to x2, my next guess. So I'd take the previous guess and I need to subtract the value of the function evaluated at 1.25. And on the bottom is the derivative evaluated at 1.25. So putting this on our calculator, we get about 1.17845 and so on. So then we do the same process again. So if we do that, we get about 1.1675. Now it turns out if I keep doing these iterations, I get 1.1673 for x4, but I also get that for x5. So that means I can be confident in my answer to 4 decimal places because I got the same answer to 4 decimal places in 2 successive iterations. So that's where I know to stop. This is correct to 4 decimal places. We're done. We've found the root. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.